Assalamualaikum warahmatullahi wabarakatuh. So, in this video, I will be showing you the solutions for Laplace equation case A. Okay, that means both ends are kept at 0 temperature. Okay, 0 degree C. Okay, we need to solve this Laplace equation, which is uxx plus uyy equal to 0 for x between 0 to A and y between 0 to B with these four boundary conditions. Okay, u0y is equal to 0, uay is equal to 0, ux0 equal to 0, and uxb equal to gx. Okay, first we need to let uxy equal to xx times y of y. Therefore, uxx equal to x double prime x y of y, and uyy equal to x of x y double prime y. Okay, next we substitute both here into the Laplace equation and separate the variable. And here we have x double prime x y of y equal to negative x of x y double prime y based on this equation. Okay, that has been rearranged into this one. Okay, and this one we do the separation of variables where x double prime x over x of x is equal to negative y double prime y over y of y is equal to p. And here, since we know that in order to satisfy the boundary conditions, we need to use p equal to negative lambda squared. Okay, it's better for you to just write negative lambda squared here, right way. Okay, and therefore we have this one. Okay, x double prime x plus lambda squared x of x equal to 0, and the other one is y double prime y minus lambda squared y of y equal to 0. Since we substitute p equal to negative lambda squared in this equation that has been derived from here to here and here to here. Okay, and so does this one. From this to here and until there. Okay, and then next we will be using the auxiliary equations, which is m squared plus lambda squared equal to 0. So m is equal to plus minus lambda I. And the next one, m squared minus lambda squared equal to 0 means m equal to plus minus lambda. Okay, therefore x of x is equal to a1 cos lambda x plus a2 sin lambda x, because the roots are complex number, and this one the roots are real and distinct, so it will be y of y equal to a3 cos hyperbolic lambda y plus a4 sin hyperbolic lambda y. Okay, next. Okay, we need to apply the boundary condition. The first one is u0y equal to 0. Means here u0y is equal to x0 y of y equal to 0 then. Okay, and here x0 equal to 0 and y of y does not equal to 0 for some arbitrary y. Just follow through to this. Okay, because y of y cannot be 0. Okay, and then next x0 is equal to 0. So we have here x of x equal to a1 cos lambda x plus a2 sin lambda x in the beginning. So substitute 0, and this one will be a1 cos 0 plus a2 sin 0. This part going to be 0, so therefore this one is equal to 1. Okay, so here we have a1 equal to 0 then. Okay, therefore x of x is equal to a2 sin lambda x. Okay, next we apply the second boundary condition uay equal to 0. So here x of a equal to 0 and y of y does not equal to 0, because again y of y cannot be equal to 0. Okay, and then x of a equal to 0, which means a2 sin lambda a. From here, okay, a2 sin lambda x will be a2 sin lambda a equal to 0. Therefore here we have a2 equal to 0, which means it will be trivial solution. Okay, so right now just write a2, sorry, wrong color. Okay, just write a2 does not equal to 0. Therefore, sin lambda a equal to 0 here. Okay, and then sin lambda a equal to 0, which means this one is equal to sin n pi. Okay, and therefore lambda A is equal to n pi over A. Okay. And for n equal to 1, 2, 3. Next. S of nx will be equal to a to n sin n pi over ax for n starting from 1, 2, 3 until infinity. And yn of y is equal to a 3n cos hyperbolic n pi y over a. Since lambda equal to n pi over a, we just need to substitute, okay, at where lambda are. Okay. N plus a for n sin hyperbolic n pi y over a for n starting from 1, 2, 3 until infinity. Okay. The next one will be the third boundary condition, which is ux0 equal to 0. Okay, which means here x of x equal to 0 or y0 equal to 0. So here x of x does not equal to 0 for some arbitrary x. Okay, so therefore we have y0 equal to 0. Okay, so y0 is equal to a3n plus 0, which means a3n equal to 0. Therefore y and y is equal to only a for n sin hyperbolic n pi y over a for n equal to 1, 2, 3 and to infinity. This one at the beginning it will be a3n cos hyperbolic 0 plus a for n sin hyperbolic 0, right? So you can use your calculator to calculate. Okay, you will find that cos hyperbolic 0 is equal to 1 and this one is equal to 0. Okay, that's why we only have a3n here. Okay, therefore unsy is equal to s of nx times y of ny, and will be as such. Okay, can be written as such. Okay, where here we can also substitute it as one constant only, capital letter an, where capital letter an is equal to a to n times a for n. Okay, this one actually we need to add another one for n equal to 1, 2, 3 until infinite. Using the superposition principle, we will have uxy equal to summation n from 1 to infinity, capital letter an sin n pi x over a sin hyperbolic n pi y over a. Okay, that means here we substitute, instead of writing in like this for n equal to 1, 2, 3 until infinity, we write it in terms of summation. Okay. And then by using the initial condition usb equal to fx, okay, usb equal to fx equal to summation here an sin n pi x a sin hyperbolic n pi y, here will be n pi dA. That means this part will be constant. Okay, we can actually factorize this part, okay, so that we know what are constants. Okay. And then from here we can see that this is a Fourier sine series. Okay, that means this one can be the substitution of the usual Bn that we calculate in Fourier sine series before. Okay, and this one an sin hyperbolic n pi b over a, we need to take this as a whole because this one refers to Bn. Okay, 2 over a integrate 0 to a fx sin n pi x over a with respect to x. Okay, and an will be written as such. Okay, and lastly you just need to substitute usy equal to this one. Okay, that means substitute the any coefficient that you have found here into this part. Okay, and this would be the final usy then. Okay, thank you. See you in the next video. Assalamualaikum.